Remember Taylor series of a function f. Taylor series of a function f is given by the form of a Taylor series. Let me make it this bigger. Okay, Taylor series. Taylor series. Taylor series of a function fx is given by so let's use tx. So it's a power series defined by at a. So this is the f derivative at a x minus c. This first two terms gives us linear approximation. Then we have higher order derivative over 2 factorial x minus a squared, etc., etc. So this is sigma f nth derivative at a over n factorial times x minus a to the power n from 0 to infinity. 0 factorial by definition means 1. 0 derivative, 0 times derivative means the function itself. Okay, and we have Maclaurin series. If a equals 0, then we get a Maclaurin series. Then we obtain the Maclaurin series. Maclaurin series. I.e. f0 plus f derivative 0 x plus f second derivative 0 over 2 factorial x squared, etc., etc., which is nth derivative at 0 over n factorial x to the power n from 0 to infinity. So this is Maclaurin series. Then right now, what we had Maclaurin series is, for instance, our Euro Maclaurin series. This is what you should really remember clearly. Okay, so e to the x, the Maclaurin series of e to the x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial, etc., etc. The general term is x to the power n over n factorial, etc., etc. Okay, so this is the x power n over n factorial, n from 0 to infinity. Okay, so this is the exponential function. You can actually, if you differentiate, you will see that this is the invariant. If you differentiate both sides, this you will see the right side. If you differentiate by power rule, you will clearly see the symmetry that is invariant under differentiation. Okay, the right side is invariant if you differentiate. It has symmetry. Okay, if you take take x to be 1, then you get the e. Okay, so you get e to be 1 plus 1 plus 1 over 2 factorial plus 3 factorial plus 4 factorial, etc., etc. Okay, so it's the 1 plus, so it's 1 over n factorial, n from 0 to infinity. Okay, then we get sine, the Maclaurin series of sine and cosine. Sine is x minus x cubed over 3 factorial plus x power 5 over 5 factorial, etc., etc. So this is the x odd power, okay, odd power factorial, n from 1 to infinity. Here we have alternating factor. Don't forget the alternating factor. -1 to the power n minus, let's use plus 1. And this from 0. Then -1 will be to the power n. To the power n. Okay, so this is sine x. Then if you differentiate, then you get cosine. Then you get a cosine. Or use definition. Cosine, this is the 1 minus x squared over 2 factorial plus x power 4 over 4 factorial minus x6 over 6 factorial, etc., etc. The general term is even factorial, okay? Factorial of even number, x to the power 2n, and then n from -1 to the power 0, to the -1 to the power n from 0 to infinity. So this is Maclaurin series for cosine. Now, what is the Maclaurin series for what is Maclaurin series for this? Ln, remember we did this, ln 1 plus x. So here x, sine, cosine, and exponential, z converges x for all real number. Okay, this x is valid for all real number. This is valid for x. It converges everywhere. Okay, converges everywhere. The radius of convergence is infinity. Now for ln, actually we know the Maclaurin series for ln, then we get x. Oops. The Maclaurin series for ln 1 plus x is x, the first term x, then the next term is x squared over 2 plus x cubed over 3. It's alternating, be careful, etc., etc. It's alternating, Okay, so it's ln. What else? We have arctangent. Arctangent x is x minus x cubed plus minus etc., etc. Okay, so this is arctangent. What else? We have this. Power. We have this. 1 plus x to the power k. This is k any real number. This is the 1 plus kx. So for ln, this x is from -1 to 1. It can be equal to 1. So here x is from -1 to it can be 1 here. 1 plus x to the power k. This is the k minus 1 over 1 times 2, x squared. Then you get a k times k minus 1, k minus 2. Then you get this is 1 times 2 times 3, so it's 3 factorial, x3, etc., etc. Okay. So general term is k minus 1, etc., etc. K minus n minus 1, x to the power n over n factorial, n from 0 to infinity. Here x is bounded by 1. It converges if x is bounded by 1. All right. Now question. We can actually derive any some other question.
Yeah.
Any questions? Okay. So this is the factors that we derived this Maclaurin series. Okay, let's see some more example. Now, can you find arc sine? Arc sine x. Find its Maclaurin series of arc sine. Remember, arc sine is this. Remember, antiderivative arc sine is this. Okay, 1 over the thing. This gives an arc sine x plus c. Okay, so if we use it, so this is actually we integrate 1 minus x squared to the power -1/2 dx. Then we use Maclaurin series for this part for this 1 plus x to the power k. Then you see 1 minus x to the squared negative. Take k to be -1/2. Okay, so this will be you write the thing. This is the 1 plus you take x to be replace x by -x squared. Replace x by -x squared. Then you get a 1. The next thing is -1/2. So this is k times x negative x squared. Okay, plus k, here k minus 1, negative 1/2 minus 1 over 1 times 2 times negative x squared. Now let's write more terms. Plus negative 1/2, negative 1/2 minus 1. So negative so 3 over 2. I think minus 1 again. Negative 5 over 2. This will be 1 times 2 times 3 over negative x squared to the power 3, etc., etc. Okay. So if you unravel definition, so the next term, maybe just one more term. So next term will be negative 1/2, negative 3 over 2, negative 5 over 2, negative subtract 1 again, negative 7 over 2. Now this will be negative x power 2 to the power 4 over 1, 2, 3, 4. Okay, 1, 2, 3, 4. 1, 2, 3, 4. So if you unravel definition, so this will be etc., etc. Oops, etc., etc. Okay, so this is the 1 plus minus 1 minus 1/2 x squared. So we want to find the general solution, So this will be the next thing will be, this is the plus. So x power 4. Denominator is 2 squared. Denominator 2 squared. So this is 1 times 3 times 1 times 2 factorial. So this is 2 to the power 1. Sorry, it's 2 to the power 2 times 2 factorial. Then the next thing is plus. Did I get a mistake? So this is actually plus. Okay. Then this we get 135 over 2 to the power 3 factorial, x to the power 6. Okay, then you get 1,357 over 2 to the power 4 times 4 factorial, x to the power 8. Okay, etc., etc. Okay, so if you write the thing, so what do we get? The general term, x to the power, you see, is x to the power 2n. There's no alternating factor anymore. So you see 2 factorial, so then this you get n factorial. Then you get 2 to the power n, Then you get this thing, you get a 2n minus 1, double factorial. Double factorial means step length is 2. And then this is n from 0 to infinity. N from 0 to infinity. Wait, n start from 0 to infinity. Okay. Okay. So we get this thing. So we get the power series, the Maclaurin series of, so 2n minus 1 factorial means double factor, 1 times 3 times 5, etc., etc., times 2n minus 1. Okay, so we get arcsine. Okay, arcsine x is n from 0 to infinity, 2n times n factorial, 2n minus 1 factorial. Okay, x to the power 2n. Okay, so we get arcsine. Any questions about arcsine? Oh, did I get a mistake? Sorry. This is not yet. So this is the we need to integrate. So we need to integrate the thing. Arcsine is the thing. Integrate. So this should be Okay, so we should use power rule again. So this actually we get n from 0 to infinity divided by 2n. So we get a 2n times n factorial 2n plus 1 over 2n minus 1 double factorial x to the power 2n plus 1. Yeah? Okay. All right. Now let's do some examples of this applications of this Taylor series. Okay, let's evaluate this thing. Example. Find this. Find the sum 1 plus ln 2 plus ln 2 squared over 2 factorial plus ln 2 cube over 3 factorial, etc., etc. Find the sum. Find the sum. Find the sum. Now you see, this is actually, remember e to the x is 1 plus x squared over 2 factorial plus x cube over 3 factorial, etc., etc. Now you take, you see, replace x, substitute x by ln 2. Then we get replace x by ln 2. Then we get 1 plus ln 2 plus ln 2 squared over 2 factorial plus ln 2 cube over 3 factorial, etc., etc. The left side we get e to the ln 2. And e cancel ln, so this actually equals 2, okay? So they think the right side converges actually to 2, okay? Okay, more example. Find the sum of the series, this series. N from 0 to infinity, -1 to the power n times pi to the 2n, 6 to the power 2n times 2n factorial. Okay, so here we have 2n factorial, so all even terms. So if you write in this term, n from 0 to infinity, -1 alternating factor. Now pi to the power 2n, 6 over power 2n. So you get pi over 6 to the power 2n over 2n factorial. Remember, in this case, that actually we have 2n factorial. Remember, if you look at the cosine actually is -1 to the power n from 0 to infinity, x power n 2n, sorry, x power 2n over 2n factorial. So this is the Maclaurin series of cosine. Then we take x to be pi over 6. Take x to be pi over 6. Then we get cosine pi over 6. Now remember, the Maclaurin series is valid. The Maclaurin series is valid for all x real numbers. Okay, so you can plug in any number for this Maclaurin series of cosine. Now this cosine pi over 6 is √3 over 2. Then we're done for this problem. Okay. Example. N from 0 to infinity, 3 to the power n over 5 power n times n factorial. Okay. Okay, once we have n factorial, so you can write it in this form. So 3 to the power n over 5 to the power n, then you write the thing 3 over 5 to the power n over n factorial, n from 0 to infinity. Remember e, we have e to the x is x power n over n factorial, n from 0 to infinity. Now here you compare n factorial with n factorial. Now x power n, 3 to the 5, 3 over 5 to the power n. So what we do is we take x to be 3 over 5. Then we get e to the power 3 over 5 equal to 3 over 5 to the power n over n factorial, n from 0 to infinity. Then we're done. Okay, then we're done. Okay, more examples. This example. N from 0 to infinity, -1 to the power n times pi to the power 2n plus 1 over 4 to the power 2n plus 1 times 2n plus 1 factorial. Okay, so here you see 2n plus 1 factorial. They are all odd. So odd, if you look at the Euro-Maclaurin series that we did above, so the odd terms that appears, actually, what we do is we use sine x. Okay, sine x. The Maclaurin series for sine x, cosine x, e to the x, ln 1 plus x, arctan x. This is the most fundamental thing that you should remember. Okay, if you don't remember, you can easily derive it in really short of time. So you should put it in your memory. It's not that hard to remember because here there is a lot of symmetry. So you don't actually, this isn't too many work to do. 0 to infinity, n minus 1. Oh, sorry, it's n. Okay, then what do we do if you compare is, you have 2n plus 1 factorial, you have the alternating factor -1 to the power n, and both start from 0 to infinity. So what you do to x is, the remaining thing is, x to the power 2n plus 1. Then the other thing you see is easily to compare. You take x to be pi over 4. Then x to that power, then you get a pi to the power and 4 to that power 2n plus 1. So we get a sine pi over 4. Now this is the convergence for all x. You don't need to worry about the convergence for this problem, for sine and cosine. Okay, now the special value, pi over 4, sine value is √2 over 2. Okay. Okay, any questions? Okay, all right. Let's see something else. Now let's do some example of Taylor series. Okay, now for Taylor series or Maclaurin series, we can actually use the Maclaurin series to compute the third thing by approximation or numerically compute the third thing. For instance, if you write sine x as x minus x cubed over 3 factorial plus x power 5 over 5 factorial minus x power 7 over 7 factorial, etc., etc. Now, for instance, if you compute the sine of y, sine y, here y is in not degree, but reading, okay, reading. Now, the left side, sine y, is translational. It's hard to compute directly. However, the right side is algebraic, okay? So the right side is algebraic. So you can compute that thing. You can compute it, directly evaluate. So this, you get y minus y over 3 factorial plus y over 5 factorial minus y over 7 factorial. 5 factorial is already, what's 5 factorial? 5 factorial is 120, okay? 7 factorial, you multiply the thing by 120 multiplied by 42, okay? So it's it's last number. So you can forget it. Forget it's 1 over 7 factorial. So this is around, if you take to be the, the first 3 digits, so this is y minus 1 over 6 plus 1 over 120, okay? So this is around 120 minus 20 plus 1. So it's 101 over 120. Okay, around. So you get really good, you get a reasonable approximation of the thing. Okay, you get a reasonable approximation of the thing. Okay. One of the problem is we actually try to, in the early history of mathematics, mathematicians, they are trying to find a convergent series of pi, For instance, we have one example derived from arctime. Remember arctime x is x minus etc., etc. This is valid if x greater than -1, less than equal to 1. Then if you plug in 1, then you get pi over 4, which is 1 minus a third plus dot dot dot. Okay, so you have a series that converges to pi. It turns out that this thing converges really slow. Converges really slow. Okay. Now, a good thing to write for a writing project is find a series that converges to pi. Converges fast to pi, fast to pi. Now the above converges to pi really slow. Okay, if you do a lot of algebra, do a lot of computation, you only get a really bad result. Okay, so writing project. Find power series that converges to pi. So if you Google this, you actually find a lot of, you should find a lot of power series that converges to pi. I think right now we already have the background. Okay, you know the power series, Taylor series. Then you can try to write a project, do a writing project on this. Okay, really good writing project. Okay. Another thing that I want to mention is maybe generating function. Okay, generating function. Generating function. I mentioned the last time about a generating function. Okay, today we will do one example of a generating function. The famous Fibonacci numbers. Okay, So we will come back. Now let's back to generating functions. Okay.
Oh.
Questions?
Oh, is that the project that we have to do like mandatory?
Right now we don't have one don't apply to. It's really hard to give you a final. You know, we will have many chances. You can choose to do this writing project, and we will write down several other writing projects. Okay, writing projects, so that you can choose. Yeah. If you don't want to do this one, you can find another. Okay.
So like a essay or
Yeah. Okay. Okay, so generating functions. Generating functions. Okay, so the idea is give a sequence. A from 1 to infinity. Now, if the sequence comes from a reasonable or very natural thing in mathematics, then we associate, then we include AN. Now, the idea is when we study something, we do not study individual objects. Okay, we don't study individual objects. We study the category of this all the objects simultaneously. Okay, then we can include AN in terms of a power series. In a power series. Okay, include the thing in a power series. GX. Okay. Okay. So GX is called the generating function of AN. The generating function. Generating function of AN. Okay. First of all, we can determine AN, recover. We can decode it. Okay. We can find AN by GX. Okay. We can find AN by GX. Okay. So, for instance, A0 is G0. Okay. Now A1 is G prime. Okay, G prime 0. But you need to be careful. Divided by 1 factorial. A2 is G prime double prime at 0 over 2 factorial. Okay, so this factorial comes from power rule. You can differentiate and then plug in 0. So that you see, once we get a G, so we have nothing lost. Okay, once we know G, okay, we can recover this AN. So nothing is lost. Okay, so we include. So the benefit of this G is we include all this sequence, all the numbers in this sequence simultaneously in this function G. Now the symmetry, some property of this AN, okay, symmetry or something is actually included to the property of the function G. And then we can try to use the function G to study the sequence AN. Now, if we know GX very well, the generating function very well by symmetry, then we can easily recover this AN. Okay, we can recover this AN. Some example. Example of generating functions. For instance, AN is 1. For all n. Then GX is 1 plus x squared plus etc. So this is geometric. So this is 1 over 1 minus x. by the summation formula for geometric series. So here x is bounded by 1. Okay. Now example, another example. An is n plus 1. Now gx, you can write gx. Gx will be a1 will a0 will be 1, a1 will be 2, a2 will be 3, a3 will be 4. Plugging in by 3, you get 4x power cube, etc., etc. Okay, so this is use closure sum n from 0 to infinity, n plus 1 x to the power n. Or if you write the thing n from 1 to infinity, Swiss index. This we actually derived. So this actually you can differentiate. This you can actually differentiate. This is derivative use power rule. This is derivative of x power n from 1 to infinity. Then we can switch this differentiation with the summation for this series. Okay. In this course. So this will be d dx. This will be use summation formula for geometric series. First term in this geometric series, first term a is x, r is x. So you write down the series, the sum of the series. And then by algebra, you differentiate the thing, then you get the thing. Okay. So we get the generating function. So we get the generating function is the thing. Okay. So a good book, a good reference of this generating function is this book, Generating Functionology. Generating, just one word. Generating functionology. This is a good book. This is a good book. This is written by the professor at UPenn, Wilf. Okay, it's a professor at UPenn. It's a really good book. It's a really good book. Okay, now let's do the Fibonacci sequence. Example. Generating function of the Fibonacci number. Fibonacci sequence. Okay, remember Fibonacci sequence is defined in this manner. F1 is equal to F2 equals 1. Then Fn plus 1 equals Fn plus Fn minus 1. So we get the sequence, Fibonacci sequence, n from 1 to infinity. Okay, this is the famous Fibonacci number. Then we try to find the gx, find the generating function of the Fibonacci number. Gx, maybe we use, let's use capital F. We just use everything special for this Fibonacci number. N from 1 to infinity. Fn x power n. Okay. Okay. Now we actually use some property, property of the Fibonacci number. Now, if you write down several terms, the first term f1 is 1. Okay, f1 is 1. So when n is 1, then we get x. Then when n is 2, then we get x squared. Now f2 is 2, so the coefficient is 1. Okay, f2 is 1. Then we get degree 3, f3 x cubed. f4 x power 4, etc., etc. Now we try to do something. Okay, we do the thing. We use the property of the Fibonacci number. So this will be x plus x squared plus f3. Use the recursive relation. f3 is the sum of the two terms before f3. Okay, so it's a f2 plus f1 x squared. Okay, oh, x cube, sorry. Then f4 is f3 plus f2, f power 4, etc., etc. Now, if you use algebra, so this will be x plus x squared plus, okay, here, if you expand this, so you get f2 x cube. Here we can switch the order of summation. So here for x small enough, this converges absolutely so that we can switch the order of summation. Okay, so this is f1. Use algebra. f3 x power x, f2 x power 4, etc., etc. Now we group it in another form. Okay. Okay. Now we group in this manner. X plus x squared. Now this term is this term. We put them together. Okay. So this is the f2 x cubed plus f3 x power 4. And then the next term comes from the power, the next term. So this is x4, this f4 times x5 plus etc., etc. Then the remaining thing we organize, group them together. So this f1 x cubed plus f2 x power 4 plus f3 x power 5, etc., etc. Now you see we can do this. This is x plus x squared. You can factor a factor of x plus factor a factor of x. So this is x, f2 x squared, f3 x cubed, f4 x power 4, etc., etc. Now this actually more or less the thing in the bracket we just write it is looks like has many terms come from the generating functions. Okay, and here for this we write as fact out x squared, f1 x, f2 x squared, f3 x cubed, etc., etc. Now this thing is actually by definition our gx. Okay, this thing is our gx. Now this thing, what is this thing? This is more or less of gx, but here we subtract the first term x. Okay, the first term is x. Okay, so we get a relation. of gx with itself. So, let's use capital F. The relation I use is capital F. Sorry. So we get capital F equals x squared plus x plus x squared plus x times capital F minus x plus x squared capital F. Okay. Okay. Now if you rearrange this, so you get x plus x squared plus x times capital F minus x squared plus x squared F. Okay. Now negative x squared cancel x squared. So this will be x plus x fx plus x squared fx. Now the left side we also have fx. So you can rearrange this. So move the terms that has fx to the left. So you get a fx minus x fx minus x squared fx is x. So if you factor out the common factor fx, then you get a y minus x squared times fx equals x. Then you can solve fx is x over y minus x squared, so that this is the generating function of the Fibonacci sequence. Okay. Now, how do we actually, if you can get a power series, okay, if you can find power series of f, then you can, if we can find the power series of f, then we can recover the Fibonacci sequence. Okay. Now we find a power series representation of fx. Remember, the generating function is a power series. Define its coefficients is the Fibonacci sequence. Okay, the Fibonacci sequence, the Fibonacci numbers. Then, if we can recover, we get a power series explicitly of capital F. Then we can get, then we recover to find an explicit formula of Fn, the Fibonacci sequence, Okay, so the question is now, how do we find a power series representation of this generating function? Okay, now how do we find, now the function that we want to study is this, the generating function is this, x over y minus x squared. How do we find a power series of the thing? How do we find a power series representation of this function? Remember, we did a similar problem last time. Okay. Now, if we have, now the denominator has three terms. Now, if the denominator has two terms, okay, what we usually do is we use geometric series. Okay. The geometric series, remember the geometric series is a over y minus r. So usually we manipulate, we choose proper factor of r and a proper factor of a, so we can get a power series, use geometric series. Now for this, unfortunately we cannot use directly. However, we can use partial fraction decomposition. Okay, we did one example use partial fraction decomposition last time. So here we use partial fraction decomposition. Use partial fraction decomposition. We use partial fraction decomposition such that we get a simple fraction that has linear factor as denominator. Partial fraction decomposition. All right. Okay, now we do this. Y minus x squared. We factor this. So this is x factor. Y plus x minus y. Okay. If you factor this, you can find two of its roots. X squared plus x minus y equal to 0. Then you find its roots. X is plus minus y. Sorry, it's negative 1 plus quadratic formula. Okay, b squared or minus 4ac. So it's y squared minus 4 times a is 1 times c is negative 1 over 2a. So this you get 2 negative 1 plus minus root 5. Okay, this is actually the golden ratio. This is actually the famous golden ratio. Okay, golden ratio. Okay. So you can write the thing as, so if you let the two roots as, let these two roots r1 to be negative 1 minus root 5 over 2, r2 to be negative 1 plus root 5 over 2. Then actually you can get x squared plus x This is x minus r1, x minus r2. Okay. Okay. So you can write as what we finally have is by partial fraction decomposition. So this will be x over negative x minus r1, x minus r2. So you can find its partial fraction decomposition. Partial fraction decomposition. Okay, partial fraction decomposition. So this will be x minus r1 a plus x minus r2 b. Okay, so we determine a and b. We determine a and b explicitly. So you multiply the denominator. You get a negative x, which you get a times multiply denominator x minus r2 plus b times x minus r1. Okay. Okay. So now we solve a and b. Now let's take x to be r1. Take x to be r1. Okay, then we get negative r1 is a times r1 minus r2, b times 0. r1 times r1, we get 0. So we get this thing, we get a r1 minus r2 plus 0. The second term is 0 on the right. Okay, so we get a is negative. So it's r2 minus r1. Oh, sorry, it's the other way around. r1 over r2 minus r1. Okay, what is a? What is r1? What is r1? What is r2? r1. So here r1 is negative 1 minus root 5 over 2. r2 minus r1 is negative 1/2 plus, excuse me, negative 1 plus root 5 over 2 minus r2, minus r1. So it's plus 1 plus root 5. Okay, so you get actually clear denominator. So a will be, this will be twice root 5 over, sorry, it's root 5 here, root 5. Then you get, this is negative 1 minus the thing over 2. Okay, b is, what is b? B is, you let x be r2. Take x to be r2. Take x to be r2. Then you get negative r2 is a times 0. You get a 0. b times r2 minus r1. Okay. Okay, so what we get is b is, so this is b times r2 minus r1. So you solve b. B is negative r2 divided by r2 minus r1. Okay, so b is, you substitute. So you get r2 is negative 1 plus root 5 minus, so you get plus. Now r2 is negative, remember r2, what is r2? Don't lose yourself. R2 is negative 1 plus root 5 over 2. So you finally get this thing is 1 minus root 5 divided by root 5. Okay, so this is actually 2 root 5, 1 minus root 5. Okay, so this will be negative 2 root 5, 1 plus root 5. AB, okay? So we find AB. Then we find the partial fraction will be, A will be, so X this will be, A will be, let's write down, copy it down A. So A will be negative So this is A. This is A over x minus R1. Remember R1. Plus B is the thing. B is y minus root 5 over twice root 5 over x minus R2. Now we can use power series to expand this thing. We can use power series to expand this thing. Use geometry series. Okay, use geometry series. Okay, so this thing will be so this thing is A, this thing is B. Okay, so you got this is the A. First, what we do is what do we do? We do this manner: A over x minus R1 plus B over x minus R2. So we divide by, so it's A over R1 negative. So it's y minus x over R1 y plus B R2 negative y minus x over R2 B this one. Okay, finally we can expand. So this is the negative A over R1 sigma x over R1 power n. Okay, n from 0 to infinity. Minus B over R2 n from 0 to infinity x over R2 to the power n. Okay, now R1 times R2. Now R1 times R2. From this relation, R1 times R2. R1 times R2 is negative 1. Okay, R1 times R2 is negative 1. You can check. So this will be negative A over R1 x power n negative 1 R2 to the power n. This will be B over R2 x power n negative R1 to the power n. Okay, negative R1 to the power n. So finally, n from 0 to infinity. Combine everything together, then what we get is the coefficients n from 0 to infinity x power n multiply. This thing we get negative A over R1 negative R2 to the power n plus negative B over R2 negative R1 to the power n. Okay, now so finally we can write down the Fibonacci number Fn. You compare coefficients so that we recovered explicit expression coefficients of the power series, the two power series. One is given by the generating function definition of the thing. This is the, and another is given by what we just computed. So you get negative A over R1, negative R2 over n to the power n, minus B over R2, negative R1 to the power n. Now remember R1, R2. If you unravel the definition, plug in A and B, plug in A and B. So what do you finally get? Some algebra here is plugging R1, R2. What do we just computed? So here A is negative 1 plus root 5 over twice root 5. B is y minus root 5 over 2 root 5. Okay, so R1, R2. R1, R2. By our choice of R1, R2. R1 is, okay, R1 is negative the thing. Negative 1 plus root 5 over 2. And then R2 is 1 minus 1 plus root 5, negative over that thing. Okay, wait, let me double check. R2 is, yes, this is right. Okay, so what do you finally get? A divided by R1, A divided by R1. So what do you finally get? A divided by R1. So A divided by R1, so square 1 plus square root of 5 cancels that thing. So this will be this 1 over root 5. Negative R2, negative R2. So this will be 1 minus root 5 to the power 2 to the power n. Okay, minus b over R2, b over R2. So what you get is b over R2. Okay, b over R2. B over R2, you can cancel that the numerator. So this will be b over R2. So this will be plus 1 over root 5. Negative R1, so this is 1 plus root 5 over 2 to the power n. Okay, so finally, so you get the thing is the Fibonacci number is 1 over root 5. The thing, you know, is golden ratio. This is the famous golden ratio. Okay. Somehow that's sign mistake probably. This should be negative. I guess it should be negative. This should be negative. You check the algebra. There's some algebra problem you need to actually fix. Yeah, be careful. We have some algebra mistake we made. Yeah, be careful. So actually, that's a sign mistake. This should be negative. Then it's correct. Somehow there's some algebra mistake to fix. Okay, so finally, you see, we get the Fibonacci number. Okay. So the general idea is use the recursive relation. The recursive relation gives us some symmetry between the sequences. And this kind of symmetry, we include the symmetry to the generating function. And then we try to use this symmetry to find a closed expression of this generating function. And then once we find the closed explicit form of the generating function, then we can use algebra technique, try to expand it, okay? Try to find its power series. Once we find its power series, then we can compare its coefficients of its power series so that we recover our original sequence, okay? So this is the idea of the generating function. Okay. Now we have 10 minutes. We have 10 minutes. Okay, 10 minutes, maybe. Okay, 10 minutes. Then let's start the next part. The Newton method. Let's start a new topic. Newton's method. Let me make this bigger. Okay, let's start a new topic, which is called Newton method. Okay, sorry. Okay, let's start the Newton method. Newton's method is a effective method to compute the root of certain functions. Okay, example. Let's see one example. Find the root of the equation x power 5 plus x minus 1 is 0. Okay, first of all, this degree 5 equation. In general, degree 5 equation cannot be solved by radical. This is the milestone of modern mathematics. Degree 5 equations cannot solve in general by radicals. So this is the work of Abel and Galois. They died really young, two mathematicians. Galois is French. Now, they prove that in general, degree 5 equations cannot solved by radicals. So we cannot solve this thing by radicals. Now we try to do numerically, find the thing numerically, find a solution numerically. So let fx be x to the 5 plus x minus 1. And then you check, this is the continuous. F is clearly continuous because polynomial, continuous everywhere. Then f, you check f0, which is 0 power 5 plus 0 minus 1. Then you get -1, which is less than 0. Now f1, 1 to the 5 plus 1 minus 1. This is actually 1 plus 1, 2 minus 1. Then we get a 1, which is positive. So by the continuity, then you see if this is 0, is this 1. This is -1, this is +1. If you plot a continuous function, then somehow, okay, if you plot a continuous function, then somehow there's one intersection x0, okay? So by IVT, intermediate value theorem, there exists a root. Let's see x0 in 0 to 1, open interval. Okay, now we will find numerically x0, what x0 is by Newton's method. Now the idea, Newton's method. Let's see the idea of Newton's method. Newton's method is the following idea. Okay, suppose we have a function here, fx. Okay, fx. This is a graph of fx. So it has a root x0 that we want to find a thing. So suppose we have some rough information about x0. So we find a point, we pick a point near this x0. For instance, we pick a point x1. Okay, x1. Okay, x1 is near x0. Then we find the point x1. The point leaves this x1 upstairs on the graph of the function. And then plot. Okay, so the general procedure is this. Okay, the first step, pick a point. Okay, pick a point. Pick a point. x1 near x0. And the second step, plot the tangent line. Plot L, the tangent line. To the curve y equals fx at x1 fx1. Okay, this point. Then you see if we plot the curve, let's plot the curve, plot tangent line. If you plot somehow it's tangent line. Okay. This tangent line L. Now the tangent line, then the intersection of L with the x-axis. Define the intersection. Let x2 be the intersection. Of line L with x-axis. i.e. x2 is L intersect x-axis. Now you see from this graph, x2 is a point. x2 lies in between x So here we have x2 is a better approximation, better approximation of the root, okay? X2 is closer to x0, so it's better. It's a better number, okay? Better approximation of the root. Then you see, then we do repeat this thing. Repeat the above to x2 to obtain x3, and then repeat x3, repeat the above process to x3, replace x3, replace x1 by x3, and then we get x4, then we get x5, etc., etc. So we expect that xn approaches x0 for reasonable functions. Okay, for reasonable functions is it converges to x0. Okay, now if you let me make it bigger. Let's look at the picture. Let's see if I can make it bigger. Okay, yeah. So you get x2, and then once you get x2, you lift it upward. So you get x. So you plot a tangent line, and then you plot tangent line. You see, okay. So the tangent line. Then the tangent line intersect at x3. You see, x3 is even close to x0 now. Then do the above to x3. Lift x3 upward, and then do the tangent line again. You see, this converges really fast. The above process usually converges quickly to the root x0. Okay, converges quickly to the root x0. Okay, so now the next step, we use this algorithm. We use this idea to find explicit thing. So you find tangent line equation L, tangent line equation of L, which is the y minus y value xy equals derivative gives you slope multiply x minus x value. So x, remember x2 is the intersection. X2 is the intersection of L with x-axis. On the x-axis, the y value is 0. So what we do is we take y to be 0. Then you get solve for x. Then what you get is 0 minus fxy equal to f derivative at xy, x minus xy. So you get divide by the coefficient, divided by the derivative. Then you get x minus xy. So you solve for x. So you get x is xy minus, the solution is exactly x2. Okay, so you get x2 is xy minus fxy over f derivative at xy. So similarly, you plug in x2. So you get x3 is x2 minus f x2 over f derivative at x2. So in general, blah, 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 blah. You do this xn plus 1 is xn minus f xn, f derivative at xn. They think it's really easy to implement in a computer package. So we do a computer package. We do a computer package. Okay. So for instance, if we let fx be x to the power 5 minus x, plus x minus y. Okay. Then find its derivative, gx to be its derivative, f dot derivative. So you get a gx, okay? So you get a derivative. Then our function hx to be x minus fx over f derivative. F derivative g here. Okay, so then you do iteration. You do iteration. Now we choose, our root x0 is between 0 to 1. So we choose our initial point. For instance, choose x1 to be 1/2. So we choose x to be 1/2. Okay, we choose the thing to be 1/2. So x1 to be, let x1 to be 1/2. Okay, then what do we do? For, let's see, yeah. We do iteration, You see, after several times, this gives us really good approximation. Okay, this gives us really good approximation. You can check that if we plug in f, the number RRXY. This is really close to 0, -8 or something. Multiply 10 to the -17, 10 to the power -17. This is really, really small number. Okay, so we get a really good approximation of the root. Okay, by numerical computation. Okay. Okay.
这你妈怎么比口音啊？我求求了。
All right, let me stop here. Any questions?
Will you post the guidelines to the written project?
Yes.
Okay. And when is that going to be due?
I will put details post the details on the canvas for the
Okay,
writing project for the extra
thank you.
performance. Yeah.
And can we do quiz corrections or is that
Yes.
okay? Thank you.
Uh-huh.